Hi everyone, my name is Lipeng Wang. I'm from the Hong Kong University of Science and Technology. Today, I will present our paper, DISL, a dataset-based distributed storage and caching system for large-scale deep learning training. Deep learning has been deployed in many areas, such as image classification, object detection, natural language processing, and recommender systems. Deep learning applications works on a large amount of data. Thus, the training datasets for deep learning are pretty large. For example, ImageNet 1K, which is a popular images dataset, has more than 1 million images, and another image dataset called OpenImage has more than 9 million images. Because of the large amount of data and the intensive computation, deep learning training takes a long time. For example, training the well-known ResNet 50 model on the ImageNet 1K dataset takes more than 30 hours in a GPU cluster. As such, how to reduce the total training time has been an important topic recently. Existing studies focus on improving the computation speed of deep learning training tasks, but ignore the optimization of data access. However, our study shows that the data access takes a significant portion of the total training, especially on large clusters. Here are two figures showing some statistics from our study on deep learning training tasks. The left figure shows the training time breakdown, including the computation time and the data access time of 5 models. In this figure, the data access time takes from 40% to 90% of the total training time, depending on the model size. With powerful hardware and the computation techniques, we expect the data access time become even more significant in the total training time. The figure on the right shows the image size and type distribution on a real-world production cluster. Most files are smaller than 128 kilobytes, and the major file type is JPEG. Based on these statistics, we propose to improve the data access time so as to improve the overall performance of deep learning training. This way, people can train deep learning models more efficiently without acquiring new hardware resources. To study the data access in DLTs, we first analyze a typical deep learning training workflow on clusters. On the left of figure are training frameworks running on workloads, usually GPU-equipped. On the right is a distributed storage and caching system. At the beginning of a training task, the training framework gets the file list of a dataset. Then it shuffles the file list to generate a random order. After that, the training framework reads the dataset in epochs. In each epoch, the files are read in batches, say 128 images a batch. Typically, a DLT takes tens to hundreds of epochs to finish training a model. For example, the ResNet 50 model takes around 90 epochs to reach the desired accuracy. All file access in these epochs are served by the underlying distributed storage and caching system. In our paper, we focus on improving the performance of the distributed storage and caching system. We observed 3 problems in existing storage and caching systems on the cluster. First, metadata access is not scalable to the large number of small files in a training dataset. Second, node failures in the global cache will affect all training tasks on a cluster and are slow to recovery due to small file reads. Third, the shuffled file access pattern incurs slow read speed on storage systems. Next, we explain the 3 problems in more detail. The first problem is the slow metadata access. There are 2 alternatives of metadata server design in existing distributed storage systems. One has separate metadata servers and data servers. For example, the last file system and the GFS stores the data and metadata separately. Another alternative distributed metadata and data on all storage servers. The metadata and data are stored together. Ceph and GlusterFS are this kind of file systems. Both alternatives have drawbacks for deep learning training tasks. The first alternative does not scale due to the centralized metadata server. In a cluster, we can deploy many GPU servers, but the metadata server cannot be easily scaled up. In the second alternative, because metadata are distributed among storage servers, we need to traverse all storage servers to get the file list in a directory. This operation is expensive in deep learning training tasks because the dataset contains millions of files. In summary, existing storage systems have poor scalability on metadata access. The second problem is about global caching systems. Where the dataset is distributed among all caching nodes, such systems are vulnerable to node failures. For example, two training tasks work on two datasets respectively, as here. If one cache node encounters failure, such as system crash or power failure, all files cached on this node will be inaccessible. A caching node failure in task 1 affects both the task 1 and task 2. To retrieve these files, the training process needs to read from the underlying storage system, which slows down the training speed. The node recovery takes a long time because of large number of small file reads. The third problem is not only small file reads, but also repeated shuffled access of small files due to the large number of training epochs. The figure on the left shows the file access pattern in DLT tasks. In each epoch, the training framework shuffles the file list and reads files in a random order. The figure on the right shows the reading speed compression of different read sizes from 1 kilobyte to 4 megabyte. The 4 megabyte size read is about 25 times faster than the 4 kilobyte size read. Although existing storage systems merge consecutive small reads into large reads, the shuffled orders of DLT tasks makes this repeated access not mergeable by existing storage systems. To solve these three problems, Diesel proposed the following solutions. First, to make metadata access scalable on clusters, Diesel employs a distributed in-memory metadata server and introduces a metadata snapshot mechanism. Second, since the global cache systems are vulnerable to node failures, Diesel introduced a task-oriented caching system that contains node failures within each DLT task. Third, to merge shuffled file reads into large reads, Diesel introduces a trunk-based shuffle method. Here is an overview of Diesel. We developed Diesel on existing storage systems and used distributed in-memory key-value database as metadata servers. Furthermore, Diesel has a metadata snapshot mechanism which helps reduce the pressure on the metadata server. It also contains a task-oriented distributed cache. Diesel supports existing training frameworks such as PyTorch, Caffe, and TensorFlow. When the dataset is loaded into Diesel, the files are merged into large chunks in the client and sent to Diesel servers. The metadata is saved in the head of each data chunk. When a Diesel server receives data chunks from clients, it extracts metadata and stores it into an in-memory key-value database. One may ask why we store metadata with data chunks. The main reason is for failure recovery of the in-memory metadata. The main memory contents may be lost, such as recently written entries, or all entries may be lost in the in-memory key-value databases when a power failure occurs. Thus, the metadata in the data chunks help reconstruct the key-value pairs in the in-memory database fast. Next, we talk about the metadata snapshot in Diesel. This figure shows how we download a metadata snapshot from Diesel. Since we merge files into large chunks when writing files into Diesel, the metadata of each file includes the chunk ID, the offset, and the file length in each data chunk. When downloading the metadata snapshot of a dataset, the Diesel client will get the dataset update time and the metadata of each file to local hash maps. After that, the Diesel will save the key-value pairs into a binary file. When starting a DLT task, the Diesel clients will load the metadata snapshot file from the distributed storage and check the update timestamp of the metadata snapshot with the Diesel server. It will tell users to download the latest metadata snapshot if the timestamp does not match. In DLT tasks, the dataset is rarely changed after being written into Diesel. Therefore, it is efficient to maintain the metadata snapshot for each dataset. After loading metadata snapshot into memory, the metadata lookup will happen in the Diesel client only. For each file read, the Diesel client gets the metadata of that file, includes chunk ID, offset, and length, and sends a read request directly to the Diesel server. Next, we talk about the task-grid distributed caching system in Diesel. Diesel deploys the task-grid distributed cache across the work nodes of a DLT task. For example, the DLT task A occupies 2 GPU nodes, and the DLT task B occupies 4 GPU nodes. The GPU nodes will form a small distributed in-memory caching system. This way, a node failure does not affect other training tasks. Such task-grid distributed caching system is automatically created and deallocated with the DLT tasks. Finally, we present the trunk-based shuffle method in Diesel. Diesel converts shuffled file reads to large trunk reads to increase the read bandwidth of the underlying storage system. In DLT tasks, the file access order doesn't matter as long as it is random. The trunk-based shuffle method generates a shuffled file order by dividing the data chunks into groups and outputs a shuffled file list to the training framework. When the training framework accesses files in the generated shuffled order, Diesel performs reads at the trunk level. In each chunk, after the first few mini-batch reads, subsequent file reads can be performed directly from Diesel client cache. This way, the small file reads become large trunk-based reads on the underlying storage system to increase I/O bandwidth. The memory requirement of the trunk-based shuffle method is small compared to the original dataset size. We tested Diesel on a small cluster with 10 GPU nodes. The Diesel runs on top of a last cluster of 6 storage servers and an in-memory Redis cluster. We compare Diesel's performance with last and an in-memory caching system, memory cache D on file writing and reading. For evaluation on the real-world training tasks, we use PyTorch as the training framework and the official PyTorch training example code. 4 well-known CNN models are then evaluated. Firstly, we evaluated the performance of file writing by comparing Diesel to the last cluster and the memory KD cluster. On 4 KB file writing, Diesel is more than 200 times faster than the memory KD cluster and 360 times faster than the last. On 128 KB file writing, Diesel is more than 17 times faster than the memory cache D cluster and 120 times faster than the last, since Diesel merges small files in the client side and sends merged data chunks to Diesel server in batches. Diesel outperforms existing systems on file writing. Secondly, we evaluated the performance of metadata access and the efficiency of our metadata snapshot method. Figure A shows that increasing the number of Diesel servers will increasing the metadata access performance when the metadata snapshot is disabled. As shown in Figure B, with the metadata snapshot enabled, Diesel achieves linear speed-up on metadata access. Figure C shows the Diesel is faster than last and the local XFS file system on metadata query response time. Next, we evaluated Diesel's task-grained distributed cache. The task-grained distributed cache achieves better performance than the existing global in-memory caching system. The code boiling time of the task-grained distributed cache is much shorter than memory cache's recovery time, even though memory cache only needs to reboot a few nodes. We then further evaluated Diesel's trunk-based shuffle method. The trunk-based shuffle method has higher read bandwidth than the last file system. It is more than 50 times faster than last and on 4 KB file reading, and more than 4 times faster than last on 128 KB size file reading. In the evaluation of real-world model training, Diesel reduces about 15% to 27% training time. For these 4 models, Diesel reduces the total training time in hours. In summary, we have introduced Diesel, a storage and caching co-design system for DLT tasks. Diesel has efficient metadata management with the support of a high-performance in-memory key-value metadata database. A metadata snapshot mechanism is introduced in Diesel to scale the metadata access and achieves linear speed-up. A task-grained distributed caching system in Diesel contains node failures within individual training tasks. And a trunk-based shuffle method converts small file reads into large trunk reads to increase the read bandwidth of the underlying storage systems. Last but not least, Diesel reduces training time in real-world DLT tasks. Thank you for attending my talk. Looking forward to having more chats on the Slack channel. Thank you.